So, Google DeepMind, the brains behind the AI system AlphaFold, which predicts protein structures, has now unveiled another remarkable AI tool, GNoME. This new tool is a game changer in the field of AI, capable of discovering hundreds of thousands, perhaps even millions, of new materials at an unprecedented pace. In this video, I'll delve into what GNoME is all about, its functioning, and the significant impact it is set to have on materials science and other areas. Alright, so GNoME is a tool designed for something pretty special in science, discovering new materials. Its full name is Graph Networks for Material Exploration, and it's all about using deep learning, a type of artificial intelligence, to figure out the structure and characteristics of new materials just from their chemical makeup. Why is this important? Well, materials play a huge role in our lives. They're in everything from the solar panels on roofs to the batteries in our phones and the chips in our computers. If we could find materials that are better, cheaper, or more eco-friendly, it could really help tackle big issues like energy storage. Normally, finding these new materials is a long and hard process. Scientists spend years mixing and testing different elements, trying to get the right combination that has the properties they want. And even when they find something that works, they might not fully understand why or how to make it even better. This is where GNoME is a game changer. It looks at all the information we already have on materials and uses that to predict new ones. It can quickly tell us if a material will be stable, the energy required to create it, and its structure. What's amazing is that GNoME can do this analysis for millions of materials in just a few hours, a task that would normally take years. GNoME and AlphaFold from Google DeepMind both use deep learning for different purposes. AlphaFold works on predicting protein shapes crucial for life, made of amino acids that fold in complex ways. GNoME, on the other hand, predicts material structures. It focuses on how atoms, the building blocks of materials, come together to form various crystal shapes. So what has GNoME achieved so far? Well, in a recent paper published in Nature, Google DeepMind and their collaborators reported some amazing results. They used GNoME to predict the structures of 2.2 million new materials, which is equivalent to nearly 800 years of knowledge. And they didn't just stop there. They also created and tested over 700 of these materials in the lab using a robotic system that can synthesize and characterize new materials automatically. And guess what? They found that GNoME's predictions were very accurate, with a success rate of over 90%. GNoME works through two main models. The first one, GNoME stability, predicts how likely a material is to be stable based on its composition. For instance, if you input iron and oxygen, it assesses if they can form a stable material. This model uses a graph neural network to process data, where it represents materials as a network of atoms, nodes connected by bonds, edges. The second model, GNoME decomposition, calculates the energy required to break down a material. It takes the material's composition and stability, like iron oxide, and figures out the energy needed to separate it back into iron and oxygen. This model uses a transformer network suited for sequential data like text to analyze the sequence of material components. Together, these models allow GNoME to evaluate a wide range of materials from simple to complex and help identify the most promising ones for further study based on their stability and decomposition energy. Now let's look at some examples of materials that GNoME has discovered. These materials, synthesized and tested in labs using robotics, show promise for use in solar cells, batteries, and computer chips. For instance, copper zinc tin sulfide, CZTS, is great for thin-film solar cells. It's cheaper and more flexible than traditional cells and excels at converting sunlight into electricity. GNoME's predictions about its stability and low breakdown risk were confirmed by lab tests. Another material, lithium iron phosphate, LFP, is ideal for lithium-ion battery cathodes used in electric vehicles and gadgets. It's energy efficient and durable, and GNoME accurately predicted its stability, which lab tests verified. Zinc tin nitride, ZTN, could revolutionize transistor manufacturing for computer chips. It conducts electricity quickly and switches efficiently between on and off states. GNoME's predictions about its structural stability and low decomposition were also confirmed in the lab. So GNoME's incredible journey into uncharted material territories shows us just how much AI can change our world. Don't forget to hit that subscribe button and give this video a like if you're as excited about this technology as we are. Thank you for watching, and I'll see you in the next one.